Okay, let's get back to the Sagaing Fault and the Sagaing Fault trenches here. So again, we chose this place where the active fault is not up against the hillside. When the active fault is on the hillside, like I showed you in the drone images farther up, you can't see individual earthquakes being buried, okay? And so if we zoom into this area, we can see where our trenches are. This is the active trace, as I'll show you more in a moment. And these are some of our trenches, the red boxes. We also trench these other features on the range front to make sure that they had not produced recent earthquakes as well, because they look like they could. See these dashed lines, we had to look at them as well. Now, when you have a sinuous fault like this, you get compression. And so remember, the Sagaing Fault is right lateral, the offsets I showed you. So this block shown by the arrow is moving this way. Whoops. Sorry about that. This block is moving this way, and this block is moving that way, and we get uplift in this area. And here is one of the detailed maps we made. And you can see this uplifted ridge here along the fault. And so the fault trace takes several steps. Around here, there's actually 2 traces, as you can see in this area here. These are alluvial fans coming out of the mountains. That's in this area. And as you can see by the shape of the topography in here, all of this is young sediment. So we came here because we knew that sediment was coming off of the mountains. The fault was rupturing here, and the sediments are lapping up on the fault zone. And you can see we trenched here, and we trenched here, and we've trenched in other places here as well. So I just want to show you why we chose this spot and how you choose a spot where you know where the active fault is and you've got young sediments bearing the earthquakes on it. If we start to look at these, we cleaned off existing exposures, and in particular, this place had a quarry, and we cleaned the walls of the quarry here. And so this was a mosaic of the quarry. And then what we do is we put a grid on the wall, and we put little flags marking the faults, and we can see the layering. And then we make the students make sketches of what they think is happening here. I took a picture of one here. And you can see, to explain the deformation, they're having an offset that's making a fault bend fold here like this. They then have deposition against the fold, and then additional slip causes that to deform. And so they first, in a sketch form, figure out what they're looking at. Again, we make exposures, and just as before, see, we have a grid on the wall. Generally, we put like a 1 meter grid on the wall, and we mark features like faults or layers or things like this. And then we take pictures of all of this. So we have this wall, we have this wall, we have this wall, and then we have the wall they're looking at here. And the students at night, they don't get to rest. The students at night make these photo mosaics, and you can see now they're mapping on the photo mosaics. Another place, there was a nice scarp here. See, the land is higher here than here. So we knew the fault formed this nice little scarp here. And when we were digging this trench here, my colleague said, "Ray, it's going to be full of water. This will not be very useful." But I said, you know, I also grew up in Southeast Asia, which I did, and I know how to deal with water. And so it filled up with water. And As you can see in the later mosaic, these are horizontal lines through here. You see the string. It's sloped downhill. We dig a hole at the end of the trench and we put a pump in it and we pumped and we pumped and we pumped for days. Once it was dry, and it did dry, and again, I like wet sites because they have less bioturbation and they preserve datable material. So I actually like to dig in wet places. And you can see the beautiful fault zone here between this block and this block. So then the students get in here, they clean off the walls, they put the grid on, they mark the fault zone and the layers and features like this. And now, then they go at night and make photomosaics. And then you can see them mapping on their photomosaics. And you can see very beautifully, this is the most recent earthquake fault zone here. And you can see a nice colluvial wedge associated with it here. In most of our sites, we see a much older and deformed Pleistocene section. You can see these ages are quite old in here. Okay, some of them are very old. And we see these wedges that have been shed off. Also, I point out the star is where we found pottery. And pottery was tremendously important because if you look, you can see all kinds of C14 ages. And let me tell you, Singapore gave me a lot of money and my students and I ran a lot of C14 samples and most of them are reworked. But look at the dates and you can see that what I'm talking about here a little bit. I need my thing. For example, here's one that's 1200. And as I'll show you in a moment, the pottery must be less than 1,000. But then you see 7,000 here and 5,000 here and 2,000, etc. Because what's happening is material is being shed off of these older beds into these wedges. And I'll show you how we deal with this in a moment. If we look at the pottery, it became very important, both because of the pattern on the pottery, and we actually dated several of the pieces of pottery that ended up being approximately 800 to 1,000 years old. And so we looked for this pattern, and here's a quote from a publication you can look at if you want. But basically, at about during the 11th century, this type of repetitive impressed leaf pattern, which you see in these pieces of pottery, became very popular. And these are mainly what we found in the trenches. Now, as it says here, later in the 13th to 15th century, the pottery became glazed. They also had this pattern, but we have not seen glazed pottery in the trenches. They were unglazed. But we know that the earliest appearance is around the 11th century. And so we know that wherever we have the pottery, we're dealing with things that are about 1,000 years or less. And we can see this when we have enough radiocarbon dates. So again, this is one of our trench logs, and this just shows some radiocarbon dates from here. And I just want you to pay attention. Notice about 5,000, 4,000, 4,000, 49, etc. So a lot of the samples are similar in age and older, probably because of something that they came off the other side. But then we see a cluster. You see 900, 800, 1,200, 850 here, okay, suggesting that this is about 800 or 900 years old, maybe 1,000 years old here. And we see this consistently in here. And we also consistently see 3 or 5 earthquake horizons. So for example, you can see that this fault cuts this wedge, this crosses the fault, the next one crosses it, And I'll show you some more examples of cross-cutting features. But essentially, we see these wedges, and there's actually soils on them. So you can see on this wedge I've written, or someone wrote, buried soil, and then there's deposit on it, and then another buried soil and deposit on it and buried soil. So if you look closely, you can tell that this wedge formed quickly and a soil formed on it, material, a soil, etc. So we're quite convinced, and I'll show you a bit more evidence, that we have 5 what we call event horizons, levels at which we think earthquakes occur in all of the trenches that formed in the last 1,000 years. Now, this is something we see commonly. This is a plot of radiocarbon age versus depth from a site I worked on, the San Andreas Fault. And you can see that at any particular depth, there's a whole range, some of them really quite old. And so this is common. We also see some that are probably way too young, and this is probably bioturbation or something, dug a hole or something. And generally, we make an age model out of the ones that are stratigraphically consistent. But this problem turns out to be really bad. Thailand, also in Myanmar, you can't do anything with a small number of radiocarbon dates. You need a lot of them because so many of them are reworked. Again, looking at some examples here. Again, this is one wall, and then this is the other wall. And so what we need to do is we've got more work that we're working on. And so we map both sides of the trench. So this is one side here, and then this is the other side, but we have to reverse it because remember, we're looking south in one case and north in the other. So we have to reverse half of them. So this one has been reversed, and then we match the layers. And in particular here, this blue is a liquefied sand layer that we see here, and we also see here. Again, we see these distinctive, like if you look at E2, how this cuts up and then is faulted. You can see if you look at E2, how it cuts up here and then is faulted. And we need to match all these units in all of our walls. So this is a fault zone, the pink. These are individual trenches and ramps to get in them. And so we have 1, 2, 3, 4, 5, 6, 7, 8, 9 walls that have been mapped. And we need to turn them into a 3-dimensional map of the thickness of the layers so that we can get the lateral slip. Remember, we're only seeing the vertical slip in the trenches. So we still have some work to do. Okay, to summarize a little bit, and let's start looking at the earthquake history here. So if we look at the earthquake history, this is Mandalay, Sagaing here. And in 1946, an earthquake ruptured farther north, and it was a magnitude approximately 7.3. Minutes later, a 7.7, the epicenter was plotted here. Remember, the global network wasn't great. And based on historic records, the blue ruptured in a magnitude 7.7. Many, many aftershocks for years, including a magnitude 7.1 that occurred in 1956. And people think that that was here. So if we zoom in a bit, our trench site is here in the middle of this place where we are near the epicenter of the 1946 earthquake, and we have the aftershock that's large enough to break the ground. Again, we have evidence for this. I'll show you the dating, and we have at least 4 similar events in the last 1,000 years. Now, we're quite lucky with the 1946-56 sequence because during the 50s and 60s, this is a plot of radiocarbon in the atmosphere versus time. The Russians and the US were blowing up all kinds of H-bombs and nuclear devices, and they filled the atmosphere with radiocarbon. And so what we do is we look at how much radiocarbon is in the sample, and that's this peak. It intersects this curve of accumulating radiocarbon, and then we can get an age range. So we actually did this for 7 samples in the top wedge. And so the deposits were shed off the 1946 and the 56 aftershock rupture, had lots of organic material, and you can look at our dates are consistent to that. So we have 1954, 58, 55, 57, 55, and the uncertainties are tiny because of this rapid accumulation of C14. This is just by chance. As you can see, the C14 is decayed again, and it was very low before this. Now, the good news is this confirms, because this is the wedge generated by these earthquakes, that we really do see our earthquake number 1 is this sequence. It also tells us, because the ages are so similar, that the wedges, including the old wedges, probably form very quickly, just like we saw from the soils. Basically, the wedge forms in literally years on the scarp, and then we develop a soil, and nothing happens until the next earthquake. Okay, the final thing I want to talk about is the lateral slip or slip rate as well. And again, I want to show you, this is a beautiful map that we made, again, from the combination of the drones and the ground-based LiDAR. But what I hope you can see is that there's a big fan here that's being offset by the fault zone, which is running here. And you can see this stream is offset. This stream is offset. And if we zoom into this area, we can see that this stream, which made this fan here, once came out here and flowed this way. You can see it actually flowed around this corner for a little bit before it broke through. Similarly, this one flowed down through here until it broke through. And so we cleaned off the walls of this and mapped these, and we dug these trenches in here so we can date the fan, the channels within the fan, and these are being dated with OSL samples that we recently were able to get out of Myanmar, and Chat in Thailand and I am working on dating these. So once we get a date for the fan and these channels, we'll have a really good slip rate story here. Similarly, down in the south where we have our ridge here, we've noticed that there's a boundary. There's black gypsum clay all exposed in this area and in this area. But in between here, it's the sediments that I showed you. And there appears to be an offset of that boundary that's about 250 to 300 meters. And we have ages of these sediments, as I showed you. So we think we can get a slip rate possibly here as well, but we don't have the results yet. Okay, so let me conclude and save some time for some questions. The first thing that I hope I've convinced you is there are incredible opportunities both to educate students and to characterize seismic hazards on active faults in Southeast Asia. I believe that geology is done in the field, as you can see, and why I've spent my life teaching these field courses. And I think that's where students really get excited and really learn. The sites are easy to find. They're generally accessible. I showed you some in Thailand and also in the eastern part of Myanmar and Laos as well. And generally, the landowners are interested in what we're doing and eager to help. Often we hire them to help dig and clean the walls, and they're always involved in asking us, what are you doing and what does it mean? And telling us stories about their grandparents talking about some earthquake, etc. People seem eager to work with us. We never have had cases where people told us to go away, which is usually what happens in the US. There's lots of datable organic material and cultural artifacts, especially the pottery. We found so many bits of pottery in here, but both are subject to reworking, and the artifacts might be discarded and buried long after they were formed. And there's bioturbation. And so you really have to look at a lot of dates and be very cautious. And that's partly why we've taken so long to come up with dates of the earlier earthquakes, is we're still trying to work out all of the details, and we're waiting for the OSL samples to give us an additional constraint to make sure that we're right about the radiocarbon we're choosing. However, given the Buddhist artifacts that were introduced in about the 11th century, cow bones from the fact that this place was agriculturally active, and this few stratigraphically consistent radiocarbon dates, we can see that there's at least 5 ground rupturing earthquakes or sequences like these in the past 1,000 years near Mandalay. So far, we're still making age models. It looks like the sequence before this one was the historic 1839 earthquake, which some people have proposed is here. It's consistent with some of the consistent C14 dates. So about a 100-year interval between these two events, and at least 5 in the last 1,000 years. So at least an average of 200, and the last interval looks more like 100. And we're working on age models to try to get these older events. And so I will stop there and would be happy to answer questions or whatever we're supposed to do right now.